Hello. I not know if there's a microphone on my thing. I would really love to know how we do the microphone. Hello. Hello. All right, I'm going to assume that there is, in fact, sound. I really hope so. I really hope there is. But, you know, just how it goes. So let me get this on the Google faster. Okay. All right, so hopefully the questions are not inverted, but you never know. So when that's thing. If you have this green book though, if you go to page 48, right at the bottom here, this is where your questions start, and it goes from 48 all the way to, page 48 to page 65. Okay, so 48 to 65. All right, so let us begin. What is that on my desk? All right, let me try to back this up a little bit. All right, so here we go, the multiple choice. All right. Which quantity is a vector? All right, so a vector is something that has magnitude and direction. All right, so if we take a look at this, electric potential difference, right, that was our letter V. Does voltage have a direction? No. Electric charge is Q. Remember, we had electrons and protons, and yes, while there are minus signs, charges are not in reference to direction, right? That minus sign doesn't tell me direction, it's just telling me what type of charge it is. And electric power, same thing, you wouldn't say, you have 20 watts of power to the right, okay? So these guys are all what we call scalars, okay? So they can only be positive numbers. And the reason why I'm making a big deal is because like almost everybody got this wrong last year. All right, so electric field is a vector quantity, okay? Because it comes from the formula E equals Fe over Q. And Fe is a vector. So keep in mind, vectors come from other vectors. Okay, so they're all kind of part of the same family. It's choice one. What is the magnitude of the eastward component of the velocity of an airplane flying at 612 kilometers per hour in the direction of 40 degrees north of east? Okay. So north of east. All right. So if we had a triangle, oops, I'm sorry. Right, this thing right here, north of east. So never eat sour watermelons. Northeast would be pointing in that direction. And then we literally, this is our resultant, right? So this is the resultant R. We want to actually make the triangle. So we're going to complete its leg. So boop, 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 that's one leg, boop, 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 that's another leg. Okay. And we want to find the eastward component. So we're looking for that right here. And so remember, the horizontal corresponds to X, which is our cosine. So we have AX equals A cosine theta. So AX equals, and I have 612 kilometers per hour times the cosine of 40 degrees. Okay, let me get my handy dandy calculator. Okay, so I have 612 times the cosine of 40. And you should get the following solution of 468. Or in this case, if we round, like in our answer choice, then we would end up getting choice number 2, 469 kilometers per hour. All right. So again, we draw in that resultant, and then we just look at our components. All right. Let's see. Number 3, a car initially traveling at 25 meters per second. Again, if you guys could like comment on the Google Classroom, like if you can't hear me, please let me know. Because I have my headphones, I have different pair of headphones in, and I don't want to be doing this if you can't hear me. So I would like to fix that up. So if you can't hear me, please comment on the Google Classroom. If you can, no worries, you don't need to comment. All right. So a car initially traveling at 25 meters per second is uniformly brought to rest as the brakes are applied over a distance 40 meters. Okay. What is the magnitude of the average acceleration of braking? Okay. So again, so right here, our final answer should be positive. However, because we are slowing down, it's very possible our acceleration might be negative. So if I were to list my givens, my VI is 25 meters per second. It's brought to rest, so my VF is 0 meters per second, and the distance I've covered is 40 meters. My unknown is the acceleration. Okay, so now I would go to my handy dandy reference table, which is at the bottom of this. Okay, I'm looking for something that has VI, VF, D, and A. So I go to page 6. Okay, VF, VI, A, and D. Look at that. So we're going to use the timeless equation. So we have VF squared equals VI squared plus 2AD. I know you're like, wow, there's really not a lot of room here. Yep, that's how it goes on the physics Regents. All right. Then we're going to substitute. So we have 0 meters per second squared equals 25 meters per second squared plus 2 times A times 40 meters. Okay. 25 squared is 625. 2 times 40 is 80 plus 80A equals 0. I want to get this whole term isolated, so I'm going to have to move 625 over there using subtraction. So I have negative 625 equals 80A. I divide 80 on both sides. So negative 625 divided by 80. I get A is equal to negative 7.81 meters per second squared. However, we again are looking for a magnitude, so choice 3 will be our solution. Okay. Number 4, a brick starts from rest, falls freely from the top of the building to the ground. As the brick falls, its acceleration. All right, we're here on Earth. We know that acceleration on Earth is constant, and that is our famous number, negative 9.81 meters per second squared. But when we release an object and it falls downwards, we're just letting go of something. So we know that its starting speed is always going to be 0 meters per second. And we know that its final speed as it hits the ground, it cannot equal 0 meters per second. So what that means is obviously we have to speed up. We can't just say at 0 meters per second. So we're going to say 1 and 2 are terrible because acceleration certainly does not increase. So we know it's constant, and we know that the speed increases, which is answer choice 3. Okay. Which object has the greatest inertia? So when you see inertia, you should think of the word mass. All right. So it doesn't matter what they're doing. So honestly, I could literally go like this because no one cares what's happening. I'm literally looking for the one with the largest mass, which I see is right here. So 2,000 kilograms is my solution. An unbalanced force is always necessary too. Okay. Unbalanced forces, right? If I were to draw a free body diagram, my FG, FN, and then I have my FA and my FF. Okay. If I have an unbalanced force, right, we have some sort of net force. That means I have an acceleration occurring in that particular direction. So it's certainly not going to be to keep a body at rest. It's certainly not going to be to keep a body moving with constant velocity. Okay, so are we changing the position of the body, or are we changing the speed of the body? Okay, and acceleration is a change in speed over time. That's what it means to be accelerating, or a change in direction. It's not necessarily a change in position, it is a change in direction. So therefore, the choice here is choice 3. Space probes launched from Earth send information back to Earth from space in the form of, okay, so space equals the vacuum, which means there is no medium. So we just have to know which waves will allow a wave to propagate without a medium. Okay, so mechanical waves, that requires a medium. Sound waves also requires a medium. Longitudinal waves also require a medium, okay? Therefore, our answers are electromagnetic waves. So anybody that you see on page 2 of that electromagnetic spectrum diagram, any one of those things can travel in space, regardless of what they're doing. Number 8, a ball is thrown from the level ground at an angle of 55 degrees above the horizontal and lands on level ground. Neglecting friction, if the ball is thrown again at the same angle, okay, same angle, but within a larger initial speed, the ball will, so let's think about this. I'm giving it more speed, right? I'm throwing it at the same exact angle, but I'm giving it a larger initial speed. So we have the choices: higher and the same distance horizontally to the same maximum height, and farther horizontally, both higher and farther horizontally, or 4, to the same maximum height and the same distance horizontally. So what you can easily do to verify this, because this information is only corresponding to the x direction, okay? If you had like your little XY chart here, right, we would have VXI, AX, DX, T tote, and then we would have BYI, AY, BYF, DY, and T1 half. Okay. So again, the angle is going to be kept the same, but you're just going to change your initial speed that's given. So you could literally do like, what if it was 5 meters? And then what if it went to 10 meters? So if we're looking about the horizontal distance, right, we're looking about dx. Let's just say we're going to say that vi is 5 meters per second for the first trial. In the second trial, vi will be equal to 10 meters per second, right? We're just going to try. Okay, so I just want to get you used to not kind of saying I have to memorize things. How can I use formulas to actually help me? So if I have ax equals a cosine theta and ay equals a sine theta, I'm just going to see what happens to both of these for my level of 5, right? So if 5 times the cosine of 55, and I get, let's say that vxi is equal to 2.87, and that vyi will be equal to 5 times the sine of 55 is 4.1. Okay, that's what we have. So now I want to see, how does this affect their height and their distance? So for x, I can put in my 0 here, so 0 meters per second squared. I have t tote. What I can do, so I have this, I know what this is, I know what this is going to be, and I also can figure that value out as well. Okay, so we're going to put dy equals, we're going to use d equals vit plus 1/2 at squared. Okay, so I'm going to plug in my I just lied, we're going to have to solve for t1/2 first before we can solve for our distance. Oh my gosh, I just used the wrong one. I'm going to say vf squared equals vi squared plus 2ad. Okay, so from there, and I'm gonna go down into this section because I don't have much space here. That's, again, one of the not so nice perks of the physics Regents, right? So we're going to say at the top, which is our final velocity, I have 0 meters per second squared equals our 4.1 meters per second squared plus 9.8, plus 2 times 9.81 meters per second squared times d, right? So 4.1 squared. All right, so we know that this side, we're going to do some subtraction. So negative 16.81 equals 19.62 d. You know what, I could have made this little minus sign. I know you're like, Miss O, you're all over the place. That's okay. I just want to show you that the minus signs will cancel out. Not that really big a deal in multiple choice right now, but negative 16.81 divided by negative 19.62 gives us a height of 0.86 meters. Okay, this was our dy. Okay, so again, what we definitely know is going to happen is that it is going to travel farther because it's moving much faster. Okay, so because it's moving much faster, it's going to travel much farther. So anything that says the same distance horizontally is no good. So 1 and 4 are no good. So it's either 2 or 3. So now we're really just going to evaluate the height again. So now we're going to use this 10 value instead. We're going to put, do the same thing, but instead of putting 4.1, we're going to do 10 times the sine of 55. So I get 8.19. So I'm going to stick 8.19 here. So I have 0 meters per second squared equals 8.19 meters per second squared plus 2 times negative 9.81 meters per second squared times d. Okay. So again, let's see, 8.19 squared is going to be positive here, but again, I have to move it to the other side of the equal sign. So I put negative 67.0761 equals negative 19.62d. So I'm going to divide. Again, I could put my minus sign, so I'll do it the right way. Negative 67.0761 divided by negative 19.62. And we see that our new height is now 3.42. So obviously we see that the height, the vertical height, increases, or the vertical distance rather. So therefore it is answer choice 3. Again, we can prove that this would be come much larger. We would just have to find time. So please understand that when you have more speed, right? Like you could be at the same angle, but you have more speed, you are going to travel further and higher. Okay, and we just proved that higher part, but the same thing goes with dx. So again, if you really wanted me to show it, we'd be finding this. So we have vf equals vi plus at. I don't have t total. I need to find t1 half first. So 0 meters per second equals 4.1 meters per second plus negative 9.81 meters per second squared times t1 half. Okay, this is just going to help me find the time, and then I'm going to plug it into our other formula for the horizontal speed. Okay, so I have 4.1, excuse me, what am I doing there? So I have negative 4.1, divided by negative 9.81. So t1 half is 0.42 seconds. So that means t tot, we're just going to multiply 0.42 by 2. So t tot equals 0.84 seconds. So now if I literally do v equals d over t, and I take my value in that I got, 2.87 meters per second equals dx over 0.84 seconds, and I multiply these things, 2.87 times 0.84, I get a dx of 2.41 meters. Okay, I'm going to do the same thing, but now I'm going to use the value that when we use 10 meters per second as our resultant speed. So from here, if you recall, this was the vertical velocity when you're shooting at 10 meters per second. So instead of me putting 4.1, I'm going to do negative 8.19, negative 8.19 divided by negative 9.81, and I get a time of 0.83 seconds. I'm literally going to do the same thing. V equals d over t. It's going to take my new value. So I'm going to have 10 cosine 55. So that's 5.74 equals dx over, oh, and I just realized that that was t1/2. Oops. So t1/2, so that means t tot is double that. So 0.83 times 2 becomes 1.66 seconds. So 1.66 seconds. So I do 5.74 times 1.66, and I get a new larger range of 9.5 meters, or range, sorry. Okay, so I just proved to you mathematically, we can see that if I increase the speed, not only is my height going to change, but also my range. All right, so that's why it's changed choice 3. Yes, it is a lot of work for one single question. I just don't recommend, you actually kind of trying to memorize relationships. Okay, if you do a little bit of math, it's not too terrible. And obviously, I just showed like a lot of units. You don't need to show units in multiple choice. All right, so awesome. So I wrote basically in number 9's area, a photon collides with an electron as represented in the diagram below. All right, so we have an incident photon. It strikes or collides with a free electron. And so this electron becomes recoiled and it causes a low photon to be emitted. Okay, right? That's what you see in the scatter photon. This is actually the Compton effect right here. So we talked about this a few weeks ago. So this is our conservation of energy and momentum. So it says after the collision, the electron recoils and the photon is scattered in another direction with a longer wavelength in the incident photon. The increase in the photon wavelength results because during the collision, the photon, okay, so there's like a lot of moving parts here. So energy of a, oh my gosh, I can't think of words. Energy of a photon, right, is corresponded directly to this frequency. And remember, you also see it like this. So wavelength is inversely related to energy. It is also inversely related to frequency. So if my wavelength gets much larger, my frequency will decrease and my energy will decrease. So that means that the increase in the photon wavelength happened because it lost energy to the electron, right? It transferred its energy to that electron, okay? So that's why we say the Compton effect shows the conservation of energy and momentum. All right, let's see. What is the weight of a 60 kilogram student on the surface of Earth? Okay, no problem. Fg equals mg, right, Ms. Clifton? Okay, so Fg is equal to 60 kilograms times our special number, 9.81 meters per second squared. So 60 times 9.81 is 588.6 newtons. So that'll be choice 4. Number 11, a 120 Newton box is pulled by a 48 Newton horizontal force across a horizontal surface at constant velocity. The coefficient of kinetic friction between the box and the horizontal surface is, all right, at constant velocity, right, forces are balanced. Okay, so that means that the net force has to equal 0. So what does that mean? So if we drew like a little free body diagram over here, so Fn pushes up, Fg pushes down, Fa, and Ff. That means that all of these forces are equal to each other in the sense of who's going horizontal and who's going vertical. So Fn equals Fg, Ff equals Fa. Okay, so they tell us, all right, that horizontal force needed to push it is 48 newtons, which also means due to the fact that it's moving constant velocity, and we know that all the forces are equal, this is also going to be our force of friction value. So we go to page 6 of the reference table, and we're looking for the formula that talks about friction. Up, I see it right there, Ff equals mu Fn. This value right here is known as its weight. Weight is the same thing as saying the force of gravity. And notice the force of gravity is equal to the normal force. How funny is that? So Ff equals mu Fn. So I have 48 newtons equals 120 newtons. Oops. the coefficient of friction, then 120 newtons. Okay, we divide 120. So 48 divided by 120 is 0.4. So that is answer choice 2. All right. A box has a mass of 10 kilograms and is at rest on a shelf that is 1.5 meters above the floor. Box B has a mass of 20 kilograms and is at rest on a shelf that is 3 meters above the floor. Compared to box A, box B has a gravitational potential energy to the floor that is, okay, so PE equals mgh. So you have 10. We know that the g is going to be the same, so we could literally put in a 1 for that. And it's 1.5 meters. Actually, I'm sorry. Like, you know what? Let's use real numbers. So 10 kilograms times 9.81 meters per second squared times 1.5 meters. That's for box A. Then B would be 20 kilograms times 9.81 meters per second squared times 3 meters. Okay, now we're going to plug that in the calculator. So 10 times 9.81 times 1.5 is 147.15. And we got 20 times 9.81 times 3. And we see that we have 588. So we're going to take this number, we're going to divide it from this number. So 588.6 divided by 147.15. So 588.6, 147. And we see the scale factor difference is 4 times as great. Number 13, a 0.10 kilogram yo-yo is whirled at the end of a length of string in a horizontal circular path of radius 0.80 meter at a speed of 6 meters per second. The magnitude of the centripetal acceleration of the yo-yo is, all right, so centripetal acceleration, it's v squared over r. I have AC equals v squared over r. So I have 6 meters per second squared over 0.8 meter. All right, so 6 squared divided by 0.8 is 45 meters per second squared. Choice 4. A 4 kilogram mass is initially at rest on a horizontal frictionless surface. A constant 2 Newton force to the east is applied to the mass for a 5-second interval. As a result of this action, the mass acquires. Okay, so let's see. So what do we have information-wise? We have the mass is 4 kilograms. VI is originally 0 meters per second. The force applied is 2 newtons. And the time in all this happens is 5 seconds. And they want to know, as a result of this action, the mass acquires. Okay. So we have a lot of things going on here. Okay. If you think about it, right, you go look in your reference table, right, and you look at your answer choices, what we're going to do here, we're going to look at our reference table, right, and we're going to find a formula, right, because we just know it was initially at rest, and we don't really know anything else about it. Okay. So we want to see like what is actually going to happen here. Right. So let's just write out some formulas that might be useful for us. So P equals mv, and we have J is equal to F net times T, and that's also equal to a change in momentum. So this question obviously didn't say change in momentum, but they did give me a force at a time, which might be, particularly useful for me in this case. All right. So after that, we're going to see, how is F related to M? Because obviously, if there was a change in speed or change in velocity, that means there must have been some sort of acceleration, right? So we know that F net equals ma. So we have this 2 Newton force, the mass of 4 kilograms, and we have A. So we divide by 4, divide by 4. We know the acceleration acting on this object is, is 0.5 meters per second squared. Okay. All right, wonderful. So we know the acceleration. So now we could know, well, what can we do with that? We can find the final velocity, okay? We have VF equals VI plus AT. So I don't know what VF is. I know I started at 0 originally. I know my acceleration is 0.5 meters per second squared. And I know I have a time of 5 seconds. So 0.5 times 5 is 2.5. So I know that my VF can only be 2.5 meters per second. So these solutions are no good right off the bat. So like I said, this question had nothing to do with the change in momentum, okay? We didn't even have that as an answer choice, so none of this could work. So that was like the trick, like, oh, wow, you have force and you have time, and you have some parts of the alternative form of the impulse formula. No, that was just a trick. So now that you have VF, you can actually multiply your velocities. Obviously, 4 times 0 is going to be 0. So let's do P equals 4 kilograms times 2.5 meters per second. So 4 times 2.5, and that gives you 10 kilogram meters per second. So we know it has to be momentum, right? But now it's like, well, what direction is it? Okay, it's traveling, or excuse me, a constant force of 2 newtons to the east. Okay, the force is going to the east. The momentum will also go to the east as well. Okay, so momentum and force will go in the same direction. Number 15, motor lifts a 1.2 times 10 to the 4 Newton elevator. That's 9 meters in 15 seconds. The minimum power output of the motor is, so again, we're working with power. Power's at the bottom. So I have a time, I have a distance, and I have newtons, which is a force, okay? So I'm gonna use P equals FD over T. So I have 1.2 times 10 to the 4 newtons times 9 meters over 15 seconds. Okay, so let me put my calculator. So parentheses, 1.2 times 10 to the 4 times 9 divided by 15 gives me 7,200 watts. All right, so if we look at that, that's answer choice 2. As the train blows its horn, which emits a uniform sound, as the train approaches a stationary observer, the observer hears a sound that, so they're getting closer. So the sound is getting closer. So that means my wavelength decreases, which means my frequency gets higher. Okay, and that means, right, frequency is going to mean it's very loud. So look, we know the frequency is going to be high, so 2 and 1 are no good. And then it says, is decreasing in amplitude or increasing? Well, if it's very loud, that means high amplitude for that sound wave. Okay, so therefore it is answer choice 4. Number 17, a wood block is pulled at constant velocity across a horizontal wooden floor. What type of energy increases in this floor block system as the block moves? All right, let's talk about it. Let's see. So it's a level floor, right? It's level. Okay. What that means is no change in PE. There is also going to be no change in kinetic energy because it's moving at a constant velocity. So it's wood on wood. So, you know, rubbing it or pushing it against the floor creates thermal energy, which is just our internal energy, right? That heat. So letter Q. All right. So again, that's heat. Number 18, total energy of 5 joules is used to move an electron from position A to position B in a uniform electric field. What is the potential difference between positions A and B? Right, so an electron, okay? Potential difference is a scalar quantity. So let's just keep that in our mind. If it's scalar, my solution needs to be positive. but I am using an electron, so that's going to have a negative sign. So I go look on page 4. Okay, potential difference. They gave me energy, which is work. Okay, so 5 joules. And I know the charge of an electron because it's on page 1. I'll say, okay, yeah, for 1 elementary charge, I see 1.6 times 10 to the negative 19 coulomb. Again, we are using an electron though. So we're just going to plop the minus sign in because that's technically more correct. So I have 5 joules over negative 1.6 times 10 to the negative 19 coulombs. So again, the solution that we're going to get is going to be having a negative sign, but we all know we are going to drop the negative sign at the end because we know that potential difference is a scalar quantity. Negative 3.125 times 10 to the positive 19 volts. So we will choose the positive version. That's no good. That's no good. That's no good. There you go. Choice 1. Number 19, a 0.14 kilogram lacrosse ball traveling west at 17 meters per second is brought to rest with a 0.21 kilogram lacrosse stick. If the force applied by the lacrosse stick on the ball is 220 newtons east, the force applied to the ball by the ball on the stick is. So let's read that last sentence again. If the force applied by the lacrosse stick on the ball is 220 newtons east, then the force applied by the ball onto the stick is. So this is their example of Newton's third law. Okay. So again, we're looking for equal magnitude, but opposite direction. So 150 makes no sense. That's the answer right there, 220, but the original force is originally going east. Equal magnitude, 220 newtons, but opposite direction means that we will be going westward. So answer choice 4. Number 20, 4 wires are tested for electrical conductivity. All wires have the same length and the same cross-sectional area, but are made of different metals. Which wire has the highest conductivity? So conductivity is a good thing. It means that electricity flows with no problem. If you also recall, conductivity is the inverse of resistivity. So it's at 20 degrees right there. I got to go look at my handy dandy chart, which is on the bottom of page 4 on the right-hand side. Resistivity is at 20 degrees Celsius. So here's what we're going to do. Conductivity is this lowercase letter called sigma. It is just 1 over rho. So you're going to take these values, put 1 in the numerator and the value of these in the denominator. So aluminum would look like the following. 1 divided by 2.82 times 10 to the negative 8. Okay, I get a really big number. So I'm going to write out all the digits, right? 354609992.91. Great. Then I'm going to do the same thing for copper. 1 divided by 1.72 times 10 to the negative 8. Okay. 5813953.88. Same thing for gold. 1 divided by gold is 2.44 times 10 to the negative 8. So this is 4098366.56. And then silver, which is 1 divided by 1.59 times 10 to the negative 8. Then I get 6289308.76. Okay, so silver is the one with the highest conductivity. Okay, so again, you're literally just taking the row values and you're just dividing them. That's all. Okay, all right. The angle of incidence for a ray of light striking a plane mirror is 20 degrees. What is the angle between the incident ray and the reflected ray? Hold on 1 second, I gotta sneeze. Oh my gosh. All right. All right, so this would be like what the picture looks like. So this is 20 degrees. We know that theta I equals theta R. So my incident angle equals my reflected angle. So this is also 20 degrees. So they want to know what's the measure of this big angle right here. Well, 20 degrees plus 20 degrees gives you 40 degrees. (22) As shown in the diagram below, mass M slides across a level, frictionless surface with speed vi, and the mass strikes the spring at position A, causing the spring to compress. When the mass is at position B, it is moving at a slower speed, Vf. Which statement best describes the energy conversion as the mass moves from position A to position B? Okay, so this is A and this is B. Some of the mass's kinetic energy is converted to elastic potential energy. All of the mass M's kinetic energy is converted to elastic potential energy. Some of mass M's kinetic energy is converted to gravitational potential energy. And the last one, all of mass M's kinetic energy is converted to internal energy. Okay. So key word is frictionless. So that means no friction, no heat is created. Thus, there's no internal energy. So we do not have to worry about that. Gravitational potential energy changes when we change height. We're not doing that. We're on a level surface, right? So no change in height. So therefore, gravitational PE is out of the picture. So which statement best describes the energy conversion as it moves from A to B? All right. So it's either some of mass M's kinetic energy is converted to elastic potential energy, right? That's the energy that's stored in the spring, or all of it is being converted into the spring. Okay, so if you pay attention to what they're saying, the mass strikes the spring at position A, causing the spring to compress. When the mass is at position B, right, it's moving just at a slower speed though. So if it completely absorbed all of the kinetic energy, that thing would have came to a complete stop, but it didn't. Okay, so therefore it is answer choice 2. Not all of it has, not all of the kinetic energy has been turned into elastic potential energy. There's still some left because it's moving with a slower speed now. Okay, so that's why you have to pay attention when you read these little blurbs, right? Number 23. The diagram below shows a magnetic compass placed between unlike magnetic poles. The north pole of the compass needle will point. Okay, so remember, with magnets, it's out of north into south. So if I had a compass right here, my north pole of the compass the thing would be pointed this way. Okay, this would be where my north is, because it doesn't want to be near the other north. Okay, so it's answer choice C. Number 24. Which circuit diagram contains a lamp that will not have current passing through it until switch S is closed? Okay, so switch is like close, open, close, open. So when it's closed, current can flow through it. When it's open, current may not flow through it. Okay, so let's take a look. If this is open, then that lamp is not going on. So when I close it, yeah, this is a basic circuit. So this is a series circuit. Let's see. When I open this right here, I still have another pathway, or excuse me, I'm going around this way. I still have another pathway to go through. So that's no good. So 3 is no good. Okay, so the battery leaves, right? It's like I bounce. So this switch does nothing for me. And same thing here. I leave, I come back around. Oh my gosh, look at that. Oh, this isn't open. This is open. Okay, no big deal. I just come back around because I'm gonna use that outer loop. Okay, so choice 1, because a series circuit only has one pathway. Number 25, the diagram below represents an electric circuit, the equivalent resistance of the circuit. All my resistors are in parallel. So 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. So I have 1 over 3 ohms plus 1 over 6 ohms plus 1 over 9 ohms. So 1 over Req is equal to the following. So 1 divided by 3 plus 1 divided by 6 plus 1 divided by 9. Okay, I get this. That doesn't do anything. I hit the fraction button, so I get 11 over 18. We know that we have to take the reciprocal, so we flip both sides. So REQ is equal to 18 over 11, which is 1.64 ohms. Okay, that's answer choice 1. An object is thrown vertically upward with an initial velocity of 9.81 meters per second. What is the maximum height reached by this object? Okay, so when something gets thrown up, okay, we know that, we actually know that VI is 9.81 meters per second squared. We know that when it reaches the top, it stops, so it slows down to 0. We also know that the A is still going to be negative 9.81 meters per second squared. So we're going to look for the letter D. We were looking at our kinematics formulas on page 6. We're looking for something that has VF, A, VI, and D. So that's the timeless equation. VF squared equals VI squared plus 2AD. So I have 0 meters per second squared equals 9.81 meters per second. I'm sorry, is it 9.81? Yeah, 9.81 meters per second squared plus 2 times negative 9.81 meters per second squared times D. All right, so we're going to do 9.81, square it. So I get 96.2361 equals negative 19.62D. That's what 2 times negative 9.81 is. Oh, I'm sorry. And because you're going to have to move this over, right? So this value is here through addition. It's positive, so you'd have to move it over. So I'm going to pop in the minus sign there so we don't have to do all that work in this limited space. So I'm going to divide 19.62 on both sides, or negative. So negative 96.2361 divided by negative 19.62. I got D is equal to 4.905 meters. Okay, so that's answer choice 2. Which type of photon has the least amount of energy? If it has low energy, that means it has low frequency. Because, right, energy and frequency go hand in hand. So I'm going to look on page 2 at my electromagnetic spectrum diagram. Which one has the lowest frequency? So this is all of our high frequency bad guys over here. So anybody on the right side has a lower frequency. So we know ultraviolet is bad for us. Visible light, that's 10 to the 14th. So that's still pretty high. Infrared is in the range right outside of the visible light, but radio is the one with the shortest frequency. Okay. Number 28. A 7.5 kilogram object moving at 20 meters per second strikes a 60 kilogram object initially at rest on a horizontal frictionless surface. The two objects sit together and move off of the speed of. So this question is an example of an inelastic collision. Okay, so this is P before equals P after. There are two objects before the collision occurs. There is one object after the collision. So we have M1V1 plus M2V2 equals M1 plus M2 times VF. We're looking to find VF. So we're literally going to plug in the information they've given us. So I have 7.5 kilograms times 20 meters per second plus 60 kilograms times 0 meters per second equals 7.5 kg plus 160 kg times VF. All right, so we know that this is going to become a 0. So we're doing 7.5 times 20. So we get, oh, I didn't realize my thing had other digits there. So we get 150. So 150 equals, and then we're going to add 7.5 plus 160. We get 167.5. 167.5 VF. We divide 167.5 on both sides. So 150 divided by our answer is well, what did I do here? Uh-oh, I think I might have made a mistake. Oh yeah, did I? 7.5 kilogram objects. Straight to 60 initially at rest. Okay. Did I do something wrong? And like, guess what? This is gonna happen on the test, and like, you're like, oh my god, you have 3 hours. 3 hours. All right. Oh, that's why. I'm like, where the heck did I get 160 from? 60, 60. I'm crazy for writing 160. I was like, what the heck? All right, so it's supposed to be 67.5. That's why I was like, that is wild. So let's do it the right way. 150 divided by 67.5 is VF is 2.22 meters per second. Okay, so guess what? Mistakes happen. And even I'm not kind of above making them. I mean, yes, am I probably rushing a little bit in this? Yes, because I have some other stuff that I got to tend to. But I did want to get this done for y'all because it does matter. So it's okay to make mistakes. Okay, if you're like, I can't find the answer, like, don't just throw in the towel. Okay, like, calm down, take a deep breath, and go look where you might have made a mistake. Okay. 29. How is the electrostatic force between two positive charges affected as the charges are brought closer together? So let's see, we got Fe equals K Q1 Q2 over R squared. So first of all, they're two positives, so they hate each other. So there's no attraction between them. So they're definitely being repelling each other. And now my denominator is getting much smaller, which means that this force increases. So the force of force of repulsion between them will increase. Number 30, what is one difference between the magnetic forces and gravitational forces? I told you this question was going to be on Regents, and here it is right now. All right, so magnetic, right? We have attraction plus repulsion. Gravitational forces, when I told you Newton's law of gravitational attraction, right? We're so lucky that we get to sit down on chairs and we don't, we get to stand on the floor. That's because there's attraction between us and that object, or really any objects with mass. Obviously, with gravitational force, we don't have repulsion, which is a really great thing. Okay, so if we look through our answer choices, magnetic forces may be attractive or repulsive, whereas gravitational forces are, well, certainly not repulsive. Okay, this isn't true. This isn't true. So it's answer choice 3. Okay, magnetic forces may be attractive or repulsive, whereas gravitational forces are always attractive. Number 31, a sound wave passes through an opening in a brick wall as presented in the diagram. An observer standing behind the wall is able to hear the sound. Oh, look at this, a definition. The spreading out of a wave as it passes through the opening is an example of, wow, look at that. So you have the wave fronts approaching a slit or an opening, and then you see the Wi-Fi symbol, right? So you see the curving of those wave fronts. That is known as diffraction, okay? And that is the perfect word for word definition. The spreading out of a wave as it passes through an opening or goes behind an obstacle or barrier. Number 32, a sound wave is emitted by a vibrating tuning fork. What is transferred as the sound wave travels to the student's ear? Mass is never transferred, ever. So therefore, it is only energy. So that is answer choice 2. Number 33, an electric current passing through a copper wire at a constant temperature would result in. So let's talk constant temperature. Means R is constant. So an increase in the resistivity or a decrease. Resistivity is a property of the material. Where in copper wire, the material is not changing. So 1 and 2 immediately eliminated. They make absolutely no sense. And number 3, the emission of photons from the wire. The emission of protons from the wire. Make that make sense. That makes, that's crazy. So the only one that makes sense is the production of a magnetic field around the wire. Remember, moving charges causes an E field to be created and a magnetic field, which we use as the beta symbol. Okay, so moving charges cause an electric field to be produced and a magnetic field. Therefore, it is answer choice 4. The velocity of an object in uniform circular motion. Uniform means that the speed is remaining constant. However, velocity is a vector. So it is not just about the magnitude, it's also about the direction. So the magnitude will be constant. However, we're going around the circle. So our tangential velocity direction will always change. So it is answer choice 1. 35. Tuning fork A starts to vibrate at 320 hertz when it is held near tuning fork B. Already vibrating at 320. Oh, I think I might have read that wrong. Tuning fork A starts to vibrate at 320 hertz when it is held near the tuning fork B, already vibrating at 320 hertz. What phenomenon is exemplified by the action of tuning fork A? So if you remember that there's an object that's at rest, and then another object that's already vibrating causes that object at rest to start vibrating, right? It's matched its natural frequency. When we see that, or when we think of something externally vibrating, causing another object at rest to cause it to start vibrating, we should be thinking resonance. Okay, that's what happened to the Tacoma Narrows Bridge. That's why an opera singer can also break the glass if they sing at the certain natural frequency of that glass. 36. A light ray with a frequency of 5.09 times 10 to the 14 hertz has a wavelength of 2.44 times 10 to the negative 7 meter in diamond. The wavelength of this light ray in sodium chloride is, okay, so we have a lot of information here, like a lot of information. So what we can do is the following. All right, we are going to use, here's my reference table. So they gave us the frequency. That's cool. They gave us one wavelength, and they gave us one material. They said it was diamond. Now they want to know the new wavelength in this new material of sodium chloride. So that's M2. So I'm going to go to my wave section, and I'm going to look for something that's a ratio. Oh, I see my absolute indices of refraction and my wavelength. I don't even need to talk about the speeds. So I'm only going to write down N2 over N1 equals lambda 1 over lambda 2. So N2 will be sodium chloride. So if we want to know that material, we're going to go to the absolute indices of refraction. Sodium chloride is 1.54. So we put 1.54. The diamond, right, if we look, is 2. Oops, wow, I didn't even see it. 2.42. So 2.42. And then lambda 1 is 2.44 times 10 to the negative 7 meter over lambda 2. That's the thing we want to solve for. So then it's crisscross applesauce, right? You're just going to cross, sorry, there goes my keys. You're just going to do some cross multiplication, right? So we have 1.54 lambda 2 equals 2.42 times 2.44 times, put my calculator in range, times 10 to the negative 7. Well, that doesn't help. That's 0 there. All right, so let me see if I get my, oops. Yeah, let me delete that. All right, cool. So I got 5.9048 times 10 to the negative 7 divided by 1.54 divided by 1.54. Lambda 2 equals. So I'm going to take this number and I'm going to divide by 1.54. So 3.83 times 10 to the negative 7 meter, which is answer choice 3. Okay. The diagram below shows resistors R1, R2, R3 connected to a 12-volt source. The current flowing through resistor 3. Okay, well, first of all, this is a series circuit. So I would write down my circuit rules probably, because I think that'll probably be helpful. So you'll look at page 4. I see that for series, I have these rules right here. So I'm going to copy those down. So we'll let you know the current remains the same. Crazy. I2 equals I3. My voltage is going to be the sum of the potential drops across each resistor, and my equivalent resistance is going to be just the sum of the individual resistors. Okay, and I want to find what's going through here, but again, it's going to be the same value because all the currents have the same thing since you only have one path. So if I were to set up my VIR chart, right, this is a nice little spot, give me a lot of room. R1, R2, R3, REQ. All right, so what do I know right now? I have 12 volts. I have R1 is 15 ohms. I have 21 ohms and I have 24 ohms. So 15 plus 21 plus 24 is 60 ohms. Oh, what do you know? If I know 2 out of the 3 pieces of information, I can now use Ohm's law. So I'm going to use V equals I times R. So I have 12 volts equals I times 60 ohms. I divide by 60, divide by 60. 12 divided by 60 is 0.2 amperes. Okay, and that's choice 4. If the charge of 25 coulombs moved past the point in the circuit in 2.5 seconds, what is the current at that point? Okay, again, we're on electricity. We're talking about current, so I'm probably going to look at for I. Charge and time, look at that. So I equals delta Q over T. So I have 25 coulombs over 2.5 seconds. So 25 divided by 2.5, and I get a current of 10 amps. That is choice 2. Which statement describes an object with constant kinetic energy? So that means mass is constant, which it better be in classical physics, and also speed is constant. Okay. So a car accelerates, obviously no good. A runner decreases her speed along a curved path, no good. A sled travels down a frictionless, steep, straight hill. So when something is frictionless, that tells us that there is no friction. And if there's no friction, that means there's definitely some sort of unbalanced force going on there, which is causing an acceleration. So that means answer choice 4 is terrible. So therefore, answer choice 3 is it. Number 40, which phrase describes a box in equilibrium? Again, equilibrium, we have balance forces. So that means you're either at rest or at constant velocity, and you certainly cannot be accelerating. So a box in an elevator slowing down as it rises vertically. That's accelerating, okay, because you're moving in the vertical direction. Box at rest on a stationary table. Seems like a good one. Box sliding down a frictionless ramp. Again, when you have no friction, you have an unbalanced force. Okay, and automatically an unbalanced force means that you are accelerating. A box in free fall. Well, we know when something is released, it's dropped at rest, and then it picks up speed over time. So that is a change in speed, thus an acceleration. So therefore, it is answer choice 2. 41. Quarks may combine to produce a meson of charge. Okay, so mesons can either only be negative 1e, positive 1e, or 0e. So 3, 1, and 2 are terrible. Only choice 4 is appropriate. The diagram below shows waves A and B as they travel through a region in the same medium. Which wave best represents the superposition? So this is the sum of the waves. Okay, that's just the way to say the resultant of waves of A and B. So A is a crest and B is a trough. So that means they're undergoing destructive interference, which means it should get smaller, right? Because they're not the same thing. So that means that sum of A is going to decrease a little bit. So A is at 2, B is at 1. So that means the new one will be only at 1 like unit of amplitude. And because A is larger than B, it is going to kind of like supersede like what side are we starting on, top or bottom. So because A is much larger in amplitude than wave B is, that superposition wave will be like above the x-axis. So it's answer choice 3. The diagrams below show the direction of wave travel and direction of medium particle vibration for different waves. Which best represents the characteristics of a sound wave? This is a wonderful question. And this gets everybody every time, okay? So you need to know that a sound wave is a longitudinal wave. And If you're like, well, how am I supposed to know if it's perpendicular or parallel? Well, first of all, I never taught you waves that went in a circle, and I never taught you waves that did this. Waves either move up and down or left and right. Okay, so these two are terrible. So this is how I want you to remember. Longitudinal is parallel to the wave's motion. The L's in longitudinal, LL equals parallel. So which one is the only one that is parallel to the wave's direction? Well, if it's up and down, right, that means it's perpendicular. So that's no good. Oh, look at that. I see two parallel lines right here. So it's choice one. Number 44. In a sample of gas, many excited hydrogen atoms are in the n=4 energy level. What is the maximum number of different photon energies that can be emitted by these atoms as they return to the ground state? So you're going to go, when you see hydrogen energy levels, you're going to go to page 3. You're going to go to hydrogen, and you're going to go to n=4. And they want to know how many different energy transitions can there be when you are in the n=4 state. So if I'm at n=4, right, and I want to go back down to the ground state, I can go from here to here. I can go from 4. So I can go, I'm going to list them. So I go 4 to 1. I could go 4 to 2, 4 to 3. Then I could go 3 to 1. Yeah. Right. 3 to 1, 3 to 2, and then I can go 2 to 1. So in total, there are 6 transitions. And that's literally me just like going from like, okay, 2 to 1, 3 to 2, then 3 to 1, then 4 to 1, 4 to 2, 4 to 3. Okay, so I counted 6 transitions. Base your answers to questions 45 and 46 in the information below on your knowledge of physics. 2 students did an experiment to measure the acceleration of a free-falling object. 1 student dropped an object from rest. The other student measured the distance fallen by the object and the corresponding time of fall. The data for the dropped object are shown. Based on the data for the dropped object, the experimental value calculated for the object's acceleration is. So they have the distance fallen and the time it fell. Keep in mind we're on Earth, so oops, alive. We don't have acceleration. I just read that's what we're actually solving for. So we're going to use, oh, I'm sorry, this is what I meant to say. VI is 0 meters per second because it is, it's free falling. That's what I meant to write. So we're looking for a formula that has D, T, A, and VI. So D equals VIT plus 1/2 AT squared. So 2.4 meters equals 0 meters per second times T of 0.71 seconds plus 1/2 times A times 0.71 seconds squared. So we'll do 0.5 times 0.71 squared. We get 0.25205A equals 2.4. This cancels out because 0 times anything. Okay, so then we're going to divide this number on both sides. 2.4 divided by gives us an acceleration of 9.52 meters per second squared, which is answer choice 2. The ideal value for the acceleration differs from the one obtained experimentally by the students. What is one probable cause of this discrepancy? So let's think about this. It was dropped. So it was not given any initial horizontal velocity, right? This has nothing to do with horizontal velocity. Literally, we're dropping it vertically, right? Literally the object goes boop, just like this. So there's nothing to do with horizontal velocity. The force of gravity was much stronger outside the building than it was inside. What kind of crazy stuff is that? So 2 is terrible too. 3, motion formulas should not be used in an experimental setting. Again, what kind of duty answer is that? You know, like let's think about what we've done the entire year in physics when we've done lab is use our formulas. So that's terrible. So 3 is terrible. And choice 4, there may have been errors in the measurement of distance or time. Yeah, I mean, like sometimes you guys make errors in measuring the distance. Excuse me. Sometimes we'd like to think we're super fast and with great reflexes. But guess what? When we're measuring time, we don't get it exactly. So therefore, it's answer choice 4. Which graph represents the motion of a free-falling object from rest near the surface of the moon? Oh my gosh, big deal, it's the moon. Okay, it's the same thing if we put Earth there. You have a d versus time, so we're looking, right, the big things is zero slope, constant slope, or non-constant. So non-constant on d versus t equals accelerating. And that's what an object in free fall should be doing, right? You're starting at zero. So VI is 0 meters per second at the top. And as you're going, we know that the final velocity cannot equal 0 meters per second at the bottom. Okay. So this has a constant slope. This is actually at constant velocity in the positive direction. This is also at, this is at constant velocity, but it's in the negative direction. Okay, so those are no good. And this is going to be our solution. Okay, because this is showing as the time increases, distance is decreasing. I'm sorry, what? Hold on one second. I just had a brain fart there. Bum, bum, bum. Yeah, I'm sorry. Yeah. So as time increases, right, we're slowly coming to a cap here. That's not true. We're looking for this one. This will always be our acceleration. So this is no good. So this is there to trick you, okay? It will always look like this graph, right? You have a positive 9.81, or sorry, 1.6 meters per second squared. This is there to trick you, okay? So choice 4, just know, if you see something curved like that, I never told you a graph that looked like that before. So don't be starting to pick that one, all right? So it's always gonna be something that looks like parabolic because it comes from our formula, D equals VIT plus 1/2 AT squared. T squared gives you that quadratic look. Number 48, the diagrams below represent the initial velocities, VI, oops, I just moved the camera a little bit, of 4, oh my goodness, why is it keep moving? Of 4 identical projectiles launched from the level ground at various angles above the horizontal. Which projectile will have the longest time of flight? Okay, remember, time of flight, oh, you can't even see me writing. Time of flight is directly related to height. And remember, 90 degrees is max height plus max time of flight. So the closer you are to 90 degrees, the higher up you're gonna, the higher up you're gonna be, and you're gonna have a longer time of flight. So therefore, if we look 30, 45, 45, these are the largest ranges, 45, 30 has nothing to do with it. So therefore, it is answer choice 4, okay? Number 49, 4 forces act in a crate on a level floor shown in the diagram. At the instant shown, the crate is, first of all, I know it has to be accelerating. That's right off the bat. I know it has to be accelerating because the forces are unbalanced. So that automatically equals an acceleration. So 3 and 4 are terrible. Because I know that it's an unbalanced force, whatever side has the excess extra force, right, the bigger force, that's where the acceleration is going to point. So 100 versus 50, my acceleration is going to point to the right. So it's going to be accelerating to the right. The graph below represents the relationship between the potential energy stored in a spring, PES, and the elongation on the spring. The value of the spring constant. Okay. So we're gonna take a point and we're gonna plug it in to our formula. Okay. So if we look at page 6, PES is 1/2 kx squared. Okay. So PES is 1/2. K, we don't know. I just lied. We're not going to plug in PES. I'm going to use this point up here. I like it. So we have 0.2 joules equals 1/2. And the elongation at this point is this 0.04 meters squared. So I have 0.5 times 0.04 squared. So I have 0.2 equals 8 times 10 to the negative 4 times k divided by 8 times 10 to the negative 4, 8 times 10 to the negative 4. I have a very tiny denominator. Okay, so that should kind of tell you that the answer is going to be large. Divided by my answer. We get k is equal to 250 newtons per meter. Okay, so that is choice 4. Okay, so I took a graph, I matched it to this formula, and then I just plugged in a point from the graph. You could have done the same thing here. This would have been 0.05 joules. Okay. Oh my goodness. Now we finally made it up to the open-ended. Oh my goodness, we did a lot just now. How crazy is that? But you know, that's the way it be. All right, so I know it's a long haul. So 51 says planet Need has a mass of 6.5 times 10 to the 23 kilograms and a radius of 2.96 times 10 to the 6 meters. The magnitude of the gravitational force of attraction exerted on a 5 kilogram object by planet Need is 7.15 newtons. When the when the object is located at a position of 5.5 times 10 to the 6 meters from the center of need. Calculate the gravitational field strength of planet Need at the position of the object. All right, they put a lot of information here. It's kind of just there to bother you, so I'm going to list all of it, and then we're going to cross out like what's actually irrelevant. So I'm going to leave this mass 1, mass 2 is 5 kilograms, and Fg is 7.15 newtons. And I guess its distance, its position is 5.5 times 10 to the 6 meters. They want to know what's the gravitational field strength. They want to know G. Okay, so like, let's think of formulas that have to little g in it. Okay, so it's like, and let's read the question again. Calculate the gravitational field strength of planet Need at the position of the object. Okay. So we're going to use G equals Fg over M. Okay, G is the thing we're solving for. So this is going to be 7.15 newtons. And this is when a 5 kilogram object, right, is located. So that's the mass we're going to use, is 5 kilograms. We're going to get that little g, 7.15 divided by 5, 1.43 meters per second squared, or newtons per kilogram, whatever you want. You could have also done this another way. If you wanted to make it more complicated, you could have used the following formula. G equals Fg over M, but then actually plug in like G equals big G M1 M2 over R squared divided by M. You know, cancel out an M, and then it really becomes G is equal to big G M1 or just M over R squared. That's kind of a lot. I don't recommend that route. I would choose something easier for sure. Number 53, 54 is shown in the diagram below. A toy car initially traveling 1 meter per second uniformly accelerates to a speed of 4 meters per second as it travels down a 5 meter long pipe. Calculate the time required for the car to travel 5 meters from the top to the slope to the bottom. Okay, so I'm gonna label what I know. Again, so you see how it's 51, 52, 53, 54, like these are your equation substitution. I say get 1 point and the solution is the next point. So we have VI equals 1 meters per second. We have VF equals 4 meters per second. And we have a distance of 5 meters. Okay. Well, the first things first, we don't have acceleration. We really need time, but we also don't have acceleration. So let's keep that in mind. So we're going to have to do first substitution because I need to find this A value. So you need a formula that has VF, VI, D, and A in it, but doesn't have T, which is VF squared equals VI squared plus 2AD. So I have 4 meters per second squared equals 1 meters per second squared plus 2 times A times a distance of 5 meters. So I have 16 equals 1 plus 10A minus 1 minus 1. So I have 15 equals 10 over A. I divide 10. My acceleration is now 1.5 meters per second squared. This is something I now know. So, but that's not even like me like solving it. Like I don't actually get any credit for that, by the way. I know it really sucks. Like what? But yeah, so just keep that in mind. So this is that real substitution that they need to see. You want a formula that has all of these things in it, or at least four of them, and then one of them is to be unknown, right? So we can use VF equals VI plus AT. So I know my 4 meters per second equals 1 meters per second plus 1.5 meters per second squared times t. I subtract 1, 3 equals 1.5 meters per second. Ooh. 1.5 times t. I divide 1.5 on both sides to get t isolated. So t 3 divided by 1.5 is going to be 2 seconds. Okay, so again, I know it seemed like, oh my gosh, that is so much work. Yeah, it really does stink, especially because like no one will get credit from this part. You'll only get credit for this part. So anything with the twos, you actually earn credit for. This was like you needed to get that in order to even get the credit. You know, to even be able to do the work that would allow you to earn credit. All right, 55, 56. Calculate the resistance of an incandescent light bulb that operates at 20 watts of power when connected to a 12-volt battery. So again, I'm going to list my givens. So I have power is 20 watts. I have volts of 12 volts, and my unknown is R. So I'm going to go to electricity on page 4. Okay, I have power, and I have volts, and I want resistance. So I'm going to use P equals V squared over R. And I'm going to just substitute. So I have 20 watts equals 12 volts squared over R. Personally, I like to make this a 1 because I like two ratios set equal to each other. So I cross multiply. So I have 20R equals 144. I divide by 20, divide by 20. So 144 divided by 20 is 7.2 ohms. Right? All right, number 57. Oh, all right, a nice little graph here. Base your answers to questions 57 through 59 on the information graph below and on your knowledge of physics. The motion of a car traveling along a straight road is represented in the graph below. Determine the average speed of the car from t equals 0 to t equals 80. Yo, when you see average speed and you see that this graph is a speed graph, average just means that 2 points, right? Because you have 2 times, right? 2 times. So choose 2 points from 0 to 8. So here and here, right? That's at 0, I was at 4. And at 8, I was at 10, right? So these are going to be the speeds that I'm going to use. And literally take the average. So what that means is, so V bar equals, we have 10 meters per second plus 4 meters per second divided by 2. Okay, so 14 divided by 2 is going to be what? And hopefully you are following along with me. It's not too terrible. It's going to be 7 meters per second. Okay, and literally just put on the line. They've already given you a unit. How nice. Then it says calculate the magnitude of the acceleration of the car from t equals 0 to t equals 8. So magnitude, right, of the acceleration, when I have a speed versus time graph, if I want to find acceleration, all graphs come from formulas. Okay, so acceleration equals delta v over t. But I don't have an acceleration graph. I have a speed graph. So I got to figure out, how do I get the V, the delta V, by itself. Put this over 1, I cross multiply. Delta V is equal to A times T. When you multiply, you're taking the area of the graph. So from 0 to 8. So this shaded region right here. So right here, if I put a line right here where I'm really emphasizing, I see a nice triangle. And then here, oops, I see a rectangle. Okay. So here's, it's like, well, what do I have to show? Well, this is what you're going to need to provide us. So your equation 1 will be the area of a triangle is 1/2 base times height. So area triangle is 1/2. The base goes from 0 to 8. So 8 seconds, because we follow the units, and the height, right, we're 4 to 10. So you do 10 minus 4. That's 6 meters per second, right? See how we started 4 and we're going to 10? This is the difference here. So we have 6 meters per second. So area of a triangle, so I have 0.5, get rid of the 0.5 times 8 times 6. I get 24 meters per second. Oh, I'm sorry. Oh my gosh. I'm sorry. LOL. This is not what they want to see. I don't even know what I was just doing right now. I don't know why I just did that. I'm so sorry. I'm jumping the gun because I'm so excited and I just want to have a go to eat a snack, but I can't because I'm devoted to this. So when you go from here to here, it's all slope. When you go backwards, so if I was going to find the displacement, or distance, that's when I would use it. So it's okay, guys. I'm cool. I like to make mistakes. It helps me learn. Hopefully, if you ever see me make a mistake, you're like, hey, man, that's terrible. What are you doing? So if I want to find acceleration, I'm actually going to take the slope, LOL. And here are my 2 points, LOL. Okay? So this is what they need to see. You're either going to write the following, and I'm going to show both ways. You ready? So slope is equal to a change in y over a change in x, which breaks down into y2 minus y1 over x2 minus x1. Or you're going to write that acceleration is equal to a change in speed over a change in time, which means that you have v2 minus v1 over t2 minus t1. One of these forms needs to be shown as your equation. I don't care which one, but one of them does. Essentially, we've just applied the deltas to the axis titles to give it its like slope definition. And then you're going to substitute. You're going to say that the slope is equal to, so at 8, right? At 8, I'm at 10. So I have 10 meters per second minus, go to 4 meters per second. Then I subtract 8 seconds minus 0 seconds. So my slope, which is equal to the acceleration, so 10 minus 4 divided by 8 is 0.75 meters per second squared. Okay, so my bad. I kind of led you down a bad track just now. You were like, what is she doing? Like I said, my mind is a little preoccupied at the moment, but it's okay though. I like catching myself making mistakes. It just kind of goes to show like nobody's kind of inept for making mistakes. All right. Number 60. A light ray is traveling through a transparent medium at a speed of 1.75 times 10 to the 8 meters per second. Determine the absolute index or refraction of the medium of this light ray. Oh, snap. Okay. Wait, let me pick up my reference table really quick. So this question, talking about the indices of refraction. So I'm going to go to page 6, and I'm going to look for a formula. This is my formula right here, n equals c over v. So n equals c over v. Speed of light, excuse me, c is the speed of light in a vacuum. So that can be found on page 1. So that's 3 times 10 to the 8 meters per second over, they're saying it moves in this new medium at 1.75 times 10 to the 8. Okay, notice that they have the same base and the same exponent. When you divide exponents, you actually subtract them. So 8 minus 8 is 0. So we're going to just do 3 divided by 1.75. Wow, that was epic fail. 3 divided by 1.75 is an index or a fraction of 1.71. So you put that on the line. If you put a unit, that's incorrect, right? The index of refraction is a naked number. Number 61. As shown in the diagram below, a ray of light traveling through medium X is incident upon a surface of medium Y. The absolute index or refraction of medium Y is greater than the absolute index or refraction of medium X. In your diagram, in your answer booklet, use the straight edge to draw a ray that can represent the path of the light in medium Y. Okay, so what's really important is that this is not like, oh my God, I have to use the protractor to make it perfect. Like, this is not even that. It's super generic what they're testing you on, right? I'm going to flip the page because I think it's a little hard for you to understand. When you see a question like this and the normal is already horizontal and they're talking about like what's the incident ray and what's the refracted ray, I want you to turn the page so that the normal is going upwards. So this is my incident ray. This is where my refracted ray will be over here. So they're saying that when the object is in medium X has a smaller, so n is smaller compared to n2, right? So when it enters the new medium, right, this has a greater index of refraction, meaning it's going to slow the light down a lot. So this will slow light down, and this will cause it to bend towards the normal. Okay, so we have to know that when n2 is greater than n1, that will happen. The bending towards the normal will be seen, right? So on our diagram, right, on our answer booklet, you're like this, we're only going to use this for this side. That's it. So, and also I recommend always using a pencil. So yeah, so we're going into medium Y, right? So this is the incident ray. It goes into medium Y. We see that, we know it's the incident ray because we see that it has the arrowhead pointing in. And as soon as it gets into medium Y, we know it's actually going to bend closer to the normal. So here it is. Okay, so I'm going to take my straight edge, and I'm going to make sure that the line that I draw is close to the normal. Okay, it just shows the bending nature. That's it. Ready? There you go. That's it. That's all you needed to show to earn 1 point. You just needed to show that it bends towards the normal because N2 is greater than N1, so bends toward normal. I'm only writing this here so that you can see why we did what we did. Obviously, you wouldn't be explaining anything to anybody in this test. You would literally just be putting down what is X of you, which is just to draw the arrow. All right, so now we're on to 6263. Oh my goodness. 6263. A tungsten wire has a cross-sectional area of 5.03 times 10 to the negative 7 meters squared and has a resistance of 1.21 times 10 to the negative 2 ohm when operated at 20 degrees. What is the length of this wire? Okay, so let's write down what we know. It's a tungsten wire. So we should be going to page 4. At 20 degrees, tungsten's resistivity is 5.6 times 10 to the negative 8. So resistivity is 5.6 times 10 to the negative 8 ohm meter. Then we know it has a cross-sectional area of 5.03 times 10 to the negative 7 meters squared and a resistance of 1.21 times 10 to the negative 2 ohm. The unknown is the length, and so our equation is going to be R equals rho times L over A. So we have 1.21 times 10 to the negative 2 ohm equals 5.6 times 10 to the negative 8 ohm meter times L over 5.03 times 10 to the negative 7 meter squared. Okay, this, like, I love this. A ratio, not a ratio. Put it over 1. Eee, cross multiply. So I'm going to have 5.6 times 10 to the negative 8 times L, and then I'm going to plug in whatever this is. So 1.21 times 10 to the negative 2 times 5.03 times 10 to the negative 7. And where did I put in the wrong minus sign? Hold on 1 second. You shouldn't end up with a minus sign here, so I know I did something wrong. Times 5.03 times 10 to the negative 7. Yeah, definitely messed up there, big time. Just trying to think, where did I make a mistake? Oh, yeah. So if you guys notice, I made a mistake right here. I didn't put a little caret symbol. So that's why I was like, why is the calculator reading it like that? So 6.0863 times 10 to the negative 9, divide by 5.6 times 10 to the negative 8, divide by 5.6 times 10 to the negative 8, and my L will be the following. So I'm going to take this value, answer, divided by 5.6 times 10 to the negative 8. And we get 0.109 meters. Okay, it doesn't really matter where you round. You could round it to 0.11. You could round it to 0.1087. It really doesn't matter, just as long as you round correctly. 6465. As shown in the diagram below, a block is hanging motionless from a vertical spring. The moment you see vertical spring, I need you to understand that the spring force is equal to the force of gravity, which causes the spring to elongate from its unstretched length of 0.2 meter to a length of 0.5 meter. The length has a spring constant of 250 newtons per meter. Calculate the magnitude of the force exerted by the block on the spring. Okay, we have a lot of information here. I'm going to write down my givens. I know that x1, the unstretched length, is 0.2 meters. I know that the stretched length is 0.5 meters. I know the spring constant is, you can see me writing, 250 newtons per meter. And the unknown is the force exerted by the block on the spring. Okay. We're looking for, what's the force of gravity? Okay. Remember, vertical spring, Fs equals Fg equals Kx equals mg. However, you have two lengths, so you have to find the change in length first, which means you're going to subtract. So delta x is 0.5 meters minus 0.2 meters. So delta x is 0.3 meters. Okay, so I have an x, I have a k, and I'm looking for this. So we're going to say that Fg is equal to 250 newtons per meter times 0.3 meters. So 250 times 0.3, we get 75 newtons. Okay. All right, this is the big bad guy that we didn't anticipate on last year's test. In an experiment, a resistor is connected to a source of varying potential difference. A voltmeter and ammeter are included in the circuit so that the current can be measured at different potential difference settings. The data table below shows the potential differences and the current measured. 66, plot the data points for the current versus potential difference. Great. So I go to my handy dandy table, and where's my pencil at? Oh no, where's my pencil? Oh, there it is. And I'm literally going, okay, at 0, I'm here. All right, at potential difference of 2, I have 0.26 amps. So this will be 0.3. So I'll be like somewhere over here. Okay, good. Boop, boop. All right, at 3 volts, I'm going to be at 0.35. So somewhere probably right here. At 5 volts, I'm going to be 0.63. So somewhere over here. And at 8 volts, I'm going to be 0.98. So probably somewhere up here. Okay. Then it says draw a line of best fit. So literally going to make sure that at least 2 of my my points get touched by this line. Okay, at least 2 of them. Okay, I'm gonna erase what it went over. So I drew a line of best fit. So 1, 2, 3, 3. 68, 69, calculate the slope of this line. Okay, so again, slope. The equation I'm going to write is delta y over delta x, and that breaks down to y2 minus y1 over x2 minus x1. So you're literally going to choose 2 points from this table. So I really love the 0, 0. That's always easy. And then I'm going to choose the next one. Like, no big deal. Okay. That's personally what I like to do. So you kind of have that choice there. Like I said, you can really choose whatever points you want. Okay. So I'm going to do 0, 0, and I'm going to do 2, 0.26. Okay, so slope is equal to, so xy, xy. So I have 0.26 amps minus 0 amps over 2 volts minus 0 volts. So I have 0.26 divided by 2. So I get 0.13 amps per volts. Okay. So here's your solution. Number 70, determine the resistance of the resistor. So remember, this is a very sneaky graph because most people say that is the resistance. I took the slope of Ohm's law, right? No, the axes are flipped. So if you want to find, right, so right now this is current over, oh my God, this is I over V is really equal to 1 over R. So what you actually have to do is take the inverse of your slope. Okay, so inverse of slope equals R. So we're going to take the 0.13 and we could turn it into a fraction, all right? And we're literally going to flip it. So now it's going to be 100 divided by 13. Or you can do 0.13 caret to the -1 power, and you'll end up getting the same thing. So the resistance, R, is 7.69 ohms. Hold on, let me see if, because I rounded. So let's see. Bum, 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 bum. Okay, yeah. All right, so hopefully there's not any questions. Sorry, I just had to take a break. I need to just drink a little bit of water. Okay. Hold on 1 second. All right, so I just want to let you know that depending on what you choose as your points, you can get a slightly different solution. So I know that like our answer of 7.69 doesn't match up with like what the book's going to give you. As long as your answer is consistent with the work that you've done, you'll end up getting the point for the question. Okay, now let's take a look at 71. We're almost done here. How exciting. Oh my gosh. An alpha particle with a charge of positive two elementary charges moving towards two oppositely charged parallel plates, as shown in the diagram below. The magnitude of the electric field strength between the plates is 5 times 10 to the 4 newtons per coulomb. Determine the magnitude of the determine the charge of an alpha particle in coulombs. Okay, so we see that it's two elementary charges. We want it in coulombs. So we know for every one elementary charge, we have 1.6 times 10 to the negative 19 coulombs. That's really 2 times 1.6, which becomes 3.2 times 10 to the negative 19 coulombs. On the diagram in your answer booklet, draw at least 3 field lines to show the direction of the electric field in the space between the charge plates. So please keep in mind, right, we always said pain. Positive away into negative. So out, in, okay? So we have to draw 3. You have parallel plates. Number 1, they have to touch the plates. So where they start and where they end, they have to make contact with the plates themselves. And they have to be equally distanced, right? So parallel plates equals equally distant. Okay, so here it doesn't really matter where you draw them as long as they are equally distant, then everybody is cool with that. Or you can even do another one, okay? So like I would literally go from here to here, add a positive into negative. Okay, so there's 1. There's 2. I'm realizing you don't even see what I'm doing. That's cool. And here's 3. Okay, so we have equally distant field lines. Okay, that's literally how you would get 3 points right off the bat. Perfect. Okay, what is the direction of the electrostatic force exerted on the alpha particle as it passes through the plates? Okay, so an alpha particle is positive. Positives hate other positives. So the alpha particle would go, you could either say a multitude of answers. You could say it goes away from positive plate. Or you can say it moves to the left. Whatever just shows that it goes away from the positive, right? An alpha particle would go right to the negative plate. Then it says calculate the magnitude of the, oh my God, I have too much stuff here. Calculate the magnitude of the electrostatic force exerted on the alpha particle by the electric field as the alpha particle passes through the electric field. Okay, so let's write down what we have so far. So we just found out the charge is 3.2 times 10 to the negative 19 coulombs. Remember, we're not allowed to use elementary charges as a unit for charge when we're talking about E equals Fe over Q. So we have that. It told us the electric field strength between the plates was 5 times 10 to the 4 newtons per coulomb, and they wanted us to find the electrostatic force. So we have Fe equals, K, Q1, Q2. Oh my gosh, what is going on? We have the formula Fe, oh my gosh, what is going on with me today? E equals Fe over Q, okay? We want to choose formulas that have everything that we need and the thing we're looking for. So we have 5 times 10 to the 4 newtons per coulomb equal to Fe over a charge of 3.2 times 10 to the negative 19 coulomb. Fe equals, I'm going to multiply these two things. So I have 5 times 10 to the 4 times 3.2 times 10 to the negative 19. I get 1.6 times 10 to the negative 14 newtons as my final solution. Okay. All right. Moving on along. 76, 77. Two students investigate transverse waves using a long unstretched spring. One student holds one end of the stationary spring while the other produces 12 waves every 4 seconds. The waves have a uniform amplitude of 0.2 meter and a distance between the adjacent crests is 0.4 meters. Okay. On the diagram in your answer booklet, draw at least one complete wave produced in the spring. So we need to worry about the amplitude, which was 0.2 meter, and the wavelength is 0.4 meter. Okay, so that means this is one full cycle of sine, right? The sine curve. Take my little pencil here, and it's going to look like the following. Okay, we're going to go up and hit the halfway point at 2. We're going to go down, and we're going to hit 4. That's it. That's all you need. Just that one simple cycle. And 78 says, determine the frequency of the waves. So remember, that's why it's so important to know the definition, because they didn't talk about anything about period. They didn't talk anything about wavelength or speed. So remember, frequency is going to be the number of waves over the amount of time it takes. So they said in the question, frequency is 12 waves every 4 seconds. So then you literally just calculate like that. So 12 over 4 is 3 hertz. You just put the number 3 on the line. Okay. And then it says calculate the speed of the wave. Well, so we have its wavelength is 0.4 meter. We have its frequency is 3 hertz. And the unknown is its wave speed. So the equation that has all of these things is V equals F times lambda. So V is equal to 3 hertz times 0.4 meters. And if you plug that into your calculator, 3 times 0.4 is 1.2 meters per second. Okay. All right, now we're on to the last part. How exciting. All right, so this is the modern physics section I keep talking about. Base your answers to questions 81 through 85 of the information below and on your knowledge of physics. Alpha particles are stable decay products of many nuclear disintegrations. An alpha particle consists of 2 protons, 2 neutrons, and a mass of 6.644 times 10 to the negative 27 kilograms. When the individual masses of the 2 protons and 2 neutrons are added, the sum is 6.695 times 10 to the negative 27 kilogram. The difference between the mass of the alpha particle and the total mass of its 4 individual component particles is called the mass defect. Determine the mass defect. See that word difference? That means subtraction. So you have to take the values of when the alpha particles together versus when you take all those pieces and you add them up. Okay, so delta M is going to be the sum of the mass of individual particles minus the mass of, you know, the like the atomic value. So the mass of the alpha particle. So delta M will be 6.695 times 10 to the negative 27 kilograms minus 6.644 times 10 to the negative 27 kilogram. So delta M, 6.695 times 10 to the negative 27 minus 6.644 times 10 to the negative 27 gives you 5.1 times 10 to the negative 29 kilogram. So 5.1 times 10 to the negative 29. 8283, calculate the total amount of energy in joules that will result from the complete conversion of this mass defect to energy. So this is modern physics for sure. We're going to use E equals mc squared. So in our givens, we have the mass is 5.1 times 10 to the negative 29 kilograms. My unknown is E. And so we're going to use the equation E equals mc squared. So my mass is 5.1 times 10 to the negative 29 kilograms. C is going to be the speed of light, and then we're square it. So 3 times 10 to the 8 meters per second squared. This is going to be 9 times 10 to the 16 if you don't want to plug it into your calculator with the square, just in case you forget. So we're going to do 5.1 times 10 to the negative 29 times 9 times 10 to the 16th. Again, the reason why I'm doing 9 times 10 to the 16th is because I don't want to do 3 times the 8 squared. Okay, and I get 4.59 times 10 to the negative 12 joules. Now what they want me to do is determine the total amount of energy that would result from the complete conversion of this mass defect to energy in mega electron volts. So I have to take my value of 4.59 times 10 to the negative 12 joules, and I have to see, is there a connection on the reference table between joules and mega electron volts? So I look at this chart. This is where my conversion factors will be. I see, okay, I see electron volt. I see mega electron volt, but that's for universal mass units, so I can't use this. But I see 1 electron volt is that many joules. So that's very helpful for me. And then, so I'm going to go from there and then use the prefixes for power of 10. So we say that for 1 electron volt, we had 1.6 times 10 to the negative 19 joules. So my joules will cancel out. I'm going to take this number and divide it by that. So I have my answer, and I divide by 1.6 times 10 to the negative 19 joules. I get this really big number, 28687500. That's crazy, and this is electron volts. I hate this. So I actually want to convert this into scientific notation because I don't like how ugly it looks. So I know that my numbers, my decimal point is back there. My new one has to go over here. 1, 2, 3, 4, 5, 6, 7. So 2.86875 times 10 to the 7 EV. And now I'm going to go look at my chart. I want to go to mega. So for every 1 electron volt, for every 1 mega electron volt, I have 10 to the 6 electron volts. So we're going to multiply this by the following. 10 to the 6 electron volts is 1 mega electron volt. We're going to take this number and we're going to divide by 10 to the 6. So I'm going to put this in parentheses, divide by 10 to the 6th power, and I get 28.6875 mega electron volts. Okay. And then number 85. What fundamental interaction is primarily responsible for holding the protons and neutrons together in the alpha particle? Protons and neutrons, strong nuclear force. Okay. So you can either write the strong force or you can write strong nuclear force. Okay. And that is the June 2024 physics Regents. It was a little spicy, but nothing super duper terrible. Okay. So hopefully you're followed along, or you will follow along, and you've come to the very end. So yes, here we are. All right. Have a wonderful rest of your day. Bye-bye.